In this video, I will teach you about alcohols and phenols. We'll go over naming alcohols, then I will do a review of some topics from last semester on how to make alcohols and how to convert alcohols to alkyl halides. Then we'll look at the reduction of carbonyl compounds to form alcohols, then a Grignard reaction, the oxidation of alcohols and phenols, and finally we'll end up with biological redox reactions. Alcohols possess a hydroxyl group, an OH group, and these are extremely common in natural compounds. So here are some examples of naturally occurring alcohols. Phenols possess a hydroxyl group directly attached to a benzene ring. Technically, phenols and alcohols are different compounds. Here are some compounds that have phenols in them, such as dopamine. This is going to be important in looking at addiction and pain relief. Also, this compound, which is present in poison ivy. Also, phenols are present in flavonoid compounds, which are compounds that I personally work with in my research. Flavonoids are polyphenolic compounds, and one example of one that I'm working with looks like this. So that has two phenol rings in the structure. And this is called naringenin. Alcohols are named using the same procedure we have used previously. You identify the parent chain, which is the longest carbon chain that includes the OH group. You identify and name the substituents. You want to assign a locant to each substituent, giving the carbon that the OH is attached to the lowest number possible. Then you list the numbered substituents before the parent name in alphabetical order, ignoring prefix except iso and cyclo. And then the OH locant is placed either just before the parent name or just before the OL suffix. So for example, here we have a 5-carbon parent chain. So we take the pentane parent name, we take the E off and add OL to indicate there is an alcohol. For this example, the parent would be hexanol. So notice here you want to use the longest chain that includes the carbon attached to the OH. So the longest chain would not be this chain going here because you would avoid the carbon with the OH and you need to include it. Then you assign a locant to each substituent, giving the carbon that the OH is attached to the lowest possible number. So if we look at this molecule, we would number from left to right because then the OH will be on carbon 2. And if we numbered this incorrect way, the OH would be on a higher numbered carbon. The locant is then placed either before the parent name or just before the suffix. So this could be either 3-pentanol or pentane 3-ol. And remember, whenever you transition from number to letter, you use a hyphen. For cyclic alcohols, the OH group is always on carbon 1. So this would be cyclopentanol, and you don't have to then indicate that it's on carbon 1 because that's assumed. This would be R33-dimethyl cyclopentanol. So you number with this being carbon 1 in this direction because that gives the next substituents the lower possible number. If you numbered in the clockwise directions, that would be at carbon 4, which is a higher number. So there's two methyl groups, therefore you say dimethyl, and they're both on carbon 3, so you use that number twice. And then you have to also indicate the stereochemistry of any chiral centers in your molecule. Common names for some alcohols are also frequently used. Isopropyl alcohol, rubbing alcohol, is the same as 2-propanol. Tert-butyl alcohol is often used instead of 2-methyl-2-propanol. And then benzyl alcohol is often the name used instead of phenylmethanol. Like halides, alcohols are often classified by the type of carbon they are attached to. If the carbon they are attached to is only attached to one other carbon, it's a primary alcohol. If that carbon is attached to 2 other carbons, it's secondary, and if it's attached to 3 carbons, it's tertiary. And we can often abbreviate this as the number with a degree symbol. When an OH is attached to a benzene ring, the parent name is phenol. And then if you have additional substituents, you would number so that the first substituent gets the lowest possible number. So this becomes 4-chloro-2-nitrophenol because an NO2 group is a nitro group. Of the commercially important alcohols, methanol is the simplest, and about 2 billion gallons of methanol is made every year. It is poisonous. If you ingested it, it will cause blindness, but it has many uses, including as a solvent, as a precursor for chemical syntheses, and as fuel. You may have heard that with some of the COVID sanitizers, there have been contaminations with methanol, and there have been warnings on the news about not ingesting hand sanitizer due to possible methanol contamination. Ethanol you're familiar with. It's produced by fermentation of grains or fruits. Industrially, it's made via an acid-catalyzed hydration of ethylene. U.S. alone, about 5 billion gallons are produced per year. It's used as a solvent, as a precursor for chemical syntheses, fuel, and it is denatured. However, for human consumption, ethanol must be suitable for drinking and is heavily taxed. Isopropanol, also known as rubbing alcohol, is made industrially from the acid-catalyzed hydration of propylene. So that's propylene, and in the presence of acid and water, you can form isopropanol. It is poisonous, but has many uses as an industrial solvent, antiseptic, and gasoline additive. The OH of an alcohol has a big effect on its physical properties. So if we look at these three molecules, notice what happens with the boiling point. With ethane, the boiling point is minus 89 degrees Celsius. When you swap out the hydrogen for chlorine, now your boiling point is 20 degrees Celsius. But with an OH group, it's now 78 degrees Celsius. So that's the boiling point of ethanol. And the reason for that is the hydrogen bonding. The hydrogen bonding, those are strong intermolecular forces that have to be broken in order for the phase transition from liquid to gas. So it takes more energy in the form of heat to break hydrogen bonds to facilitate that phase transition. Alcohols with 3 carbons or less tend to be miscible in water, meaning they mix with water. Alcohols with large carbon chains do not readily mix with water and will form 2 layers if you try to mix them with water. Alcohols can be deprotonated with a strong base, and in comparison to an alcohol, a phenol is more acidic by 8 pKa units, which means 10 to the 8th, which is millions of times more acidic. And the reason for this is that if you look at the conjugate base formed of phenol, it's resonance stabilized. And generally speaking, the stronger the acid, the weaker its conjugate base. So the conjugate base of phenol, due to its resonance stabilization, is a lot weaker than the conjugate base of cyclohexanol, which explains the acidity difference. Last semester, we mentioned 3 different ways from alkenes to create alcohols. One was to use acid and water. However, that had a lot of drawbacks, including rearrangements that can take place. The other was the oxymercuration-demercuration, which followed Markovnikov's rule, and the third was hydroboration oxidation, which followed anti-Markovnikov selectivity. So recall here that the OH is on the less substituted carbon of the starting alkene, and here the OH is on the more substituted carbon of the starting alkene. Also, last semester, we talked about converting alcohols to alkyl halides. So if you have a tertiary alcohol, you can use HBr or HCl to convert that to the halide. So here we have T-butyl alcohol. We can use HBr to convert that to the bromide. If instead we wanted to convert it to the chloride, we would have used HCl. Also, as a review, last semester, I mentioned that primary and secondary alcohols can also be converted to alkyl halides, but you have to use different reagents. To convert to the chloride, you use SOCl2 called thionyl chloride, which is a sulfur double bonded to oxygen and bonded to 2 chlorines. And then the PY stands for pyridine, which is going to act as a base in the mechanism. It's essentially a benzene ring, but with a nitrogen in place of one of the carbons. And then PBr3 is how you convert a secondary or primary alcohol into the bromide. Now, the new method that you're going to learn is how to prepare alcohols via a reduction reaction. And in particular, we're going to reduce a carbonyl. Reductions involve a change in oxidation state. An oxidation state is simply a method of electron bookkeeping. To determine the oxidation state of an atom, imagine the electrons in the bond as a lone pair on the more electronegative atom. So here, if we look at methanol, if we treated all bonds as purely covalent, we would break them homolytically and give every atom one of the two electrons. But instead, let's treat them as ionic and give both the electrons in each bond to the more electronegative atom. So if we do that, carbon is more electronegative than hydrogen, so it would give all of the electrons in the bonds with the hydrogen, but oxygen is more electronegative than carbon, so it would get those two electrons. Now, how do you figure out the final oxidation state? Well, you look at the number of electrons around the carbon, so in this case it's 6, and you subtract that from the number of electrons carbon will naturally have, which you get from the column that it's in the periodic table, so the number of valence electrons. So that would be 4. So 4 minus 6 equals minus 2, therefore that carbon has an oxidation state of minus 2. So a carbon's oxidation state can range from minus 4 to plus 4. If it's oxidizing, then it's going to be going to a higher oxidation state, so from left to right. If it's getting reduced, then it's going to a lower oxidation state. So if we look at formaldehyde, for example, and we use the strategy I just showed you, we're going to have carbon keep the 2 electrons that it had with hydrogen, and then oxygen, because oxygen is more electronegative than carbon, will keep both of the electrons that were in each of the 2 bonds it had with the carbon, and it already had 2 lone pairs. So in this example, carbon has 4 electrons, it's owning 4 electrons, so 4 subtracted from the valence, which is 4, is 0. So that's an oxidation state of 0. So converting a carbonyl to an alcohol requires a reducing agent. That's something that facilitates a reduction. If something's reduced, then something must always be oxidized. The two go hand in hand. So in this type of a reaction, whatever the agent is oxidized in the process. There are 3 reducing agents that can be used. The first is hydrogen gas with a metal. However, this is rarely used because very high temperatures and pressures are required. And you may recall that we did use this in converting double bonds to single bonds last semester. The next 2 are what are called hydride reagents. A hydride is simply a hydrogen with 2 electrons and a negative charge. So with sodium borohydride, we can convert aldehydes and ketones into the corresponding alcohol. So sodium borohydride is the active reagent, and then we typically use one of these solvents. Sodium borohydride is a source of hydride, H-, which does a nucleophilic addition to the carbonyl carbon, followed by a proton transfer from the solvent. So in this reaction, the hydride is going to be delivered from the reagent to the carbonyl carbon, and then simultaneously these 2 electrons form a 3rd lone pair on the oxygen. Now you can think of this mechanism as just being H-, even though it is connected to the boron atom in the reagent. It is easier to think of these mechanisms as an H- acting freely to attack the carbonyl carbon. And why would it attack the carbonyl carbon? Tell me in the chat why you think it would attack, why H- would be attracted to the carbonyl carbon. So you get to this intermediate, which then grabs a proton from the solvent. If you have an unsymmetrical ketone, you can get a chiral center, and you will get both enantiomers. The second type of hydride reagent is lithium aluminum hydride, often abbreviated as LAH or like this. And this is a very strong reagent. It's stronger than sodium borohydride. So in this example, it is also reducing an aldehyde to the corresponding alcohol. And if you look at the structures of the reagents, they're very similar. They both have a central atom. In this case, it's aluminum surrounded by 4 hydrogens. With sodium borohydride, you have a boron in the center. But LAH is much more reactive than sodium borohydride. Because it's so reactive, it can't be used in the presence of a protic solvent, and the proton source has to be added after the carbonyl is reduced. So the same mechanism here, the hydride attacks the carbonyl carbon, and those 2 electrons form a third lone pair. And then after that's completed, then you can add water or some proton source to get the hydrogen on the O-. And there are a wide variety of hydride reagents that can be fine-tuned by using various R groups on the aluminum or the boron. Okay, I want you to go to the website organicchemistry.data.org. I have it typed in here into my Google search. It's going to come up as probably the first hit, and then you're going to see this screen. Now I want you to go into reaction info. Okay, and then we're going to see a lot of different topics here. I want you to go to reduction and oxidation. That's what this video is talking about. Now on the left, you see a lot of different topics. We're going to focus on the hydrides, aluminum hydrides, boron hydrides, silicon hydrides. And I want you to choose any of those 4 and go into it and just first look at how many different types of hydride reagents there are and how many types of reactions there are. And then from any of this information, I want you to choose one of the reactions that's discussed and shown, describe what the reagent is that's used and what the reaction is. So in particular, I would want you to discuss what is the functional group transformation. So if we look at this Lusch reduction, we have a cyclohexenone. So it has an alkene and a carbonyl. And when they use sodium borohydride, they get a mixture of those 2 products. But when they add cerium chloride, they only get reduction of the carbonyl. And that is a famous reaction called the Lusch reaction. So go in here, search for yourself, find something, and discuss it in the chat.